Okay.
Green light?
Green light. Yeah.
Great. Okay.
Okay. All right. I'll give you a minute.
Okay. Very careful.
Yes. Sure.
We have so there's a bunch of activities around the city, but in particular there'll be firework. Well, so first on the website there's actual some detailed links for events, but there'll be fireworks, after dark right here at the Folsom Stadium. That's free of charge. You just go there, and I think there's a music festival at the amphitheater close to downtown. So, and that information is on the website. I just wanted to let you know. So that's one. And the other thing I wanted to say is July and August, all the transportation, which is buses, is free in Denver and Boulder area. So take advantage of that. We probably discovered that coming from the airport. We take the money right now. It's actually everywhere around the city.
Yeah. Okay. Okay. So keep going. I guess yesterday we talked about flow case systems. I was primarily thinking about field level systems like qubits driven by periodic drives. We set up a frequency lattice way of thinking about it and went over quickly under the assumption that you've seen it before, how you get physical phenomena out of that way of thinking. And today I want to start to make the step from one to many, that is going from one drive to many drives. I'll start on the board to just generalize the frequency lattice. I know several of you have already know exactly how it's going to go, so that'll be quick. I'll move to slides just for this lecture. We'll go back to the board in the for lecture 3. Okay, so from one to many is just me adding more indices for things. So now instead of simply having a static piece plus one part of the Hamiltonian that has a periodicity set by the period of drive 1, there is a second drive, possibly more. And the assumptions we're going to make are that all these frequencies are not rationally related to each other. So we'll use the word incommensurate. Sometimes we'll also use the word quasi-periodic. When we use those words, this is what we mean. And the second thing we're going to assume, because that's what we're going to focus on a set of phenomena when these are true, is that all the frequencies we use for driving are all comparable to one another. Okay. So there's no separation of scales. And I say that just because we didn't go into it in detail, but probably some fraction of you run into what's known as a rotating wave approximation before. It is a time-dependent transformation that you can do where you describe the dynamics in a frame that's moving in time. Often this simplifies your life a lot because when you have a hierarchy of scales, certain terms will be oscillating much faster than others, and you can organize your physics that way. And we're not going to do that today. So by having all these comparable, we're really trying to look at effects of multi-tone driving. Okay, so that's that. And physical examples are, anything we said yesterday, add an extra tone. For the purposes of what we'll talk about more today, it is a multi-cavity. So for concreteness, 2 cavities connected to a qubit, where there 2 fundamental frequencies, say, which are the ones that are strongly coupled to the qubit, are satisfy these properties. Okay, and the goal of today's lecture is that I'll give you a punchline so you know what's coming. I want to demonstrate that we can have new driven phenomena with such systems, specifically that we can get quantized energy pumps whose origin lies in topological invariance that we'll discuss. And this will set the stage for lecture 3, where really we'll start to talk about new driven phases, not just phenomena. Okay, so we'll make this leap. Today I'll come to it, the details, whether, you know, are these in the steady state, are these only long lived responses, and then we'll go more abstract in the third lecture. Okay, so I just need one word actually before I finish. So our primary tool in starting to uncover these phenomena is just the frequency lattice generalized to more numbers of tones. So it's absolutely identical to how I derived it yesterday. So just to set up notation, we're now thinking about what we would call a theta vector torus. This is simply a, if I have n tones up there, this is parametrizing a point on the n-dimensional torus. It is telling us what is the phase of drive 1, drive 2, drive 3, etc. at this time. Now with that notation, we say we have a general Hamiltonian that's periodic along each of these dimensions, right? And we do the same thing we tried to do yesterday. We say, and now this is only a try. There is no flow case theorem that guarantees it, but we're going to try to find solutions to the time-dependent Schrodinger equation, which are exactly of the form that we said. They, up to a phase, the solutions we want reflect the periodicity. So sorry, I should write T here. And that's because of this phase, which is not periodic in the drives. So we're looking for solutions that up to a phase exhibit the same periodicity of all the drives. Okay, that's the change we're doing. And then we do the same things we did. And I'll go to that board. We'll plug that into the time-dependent Schrodinger equation, and we derive basically. Remember, I had this notation K to refer to a hopping, a generalized type binding model on the frequency lattice. So the kinds of Hamiltonians we then will obtain will describe hopping models in n dimensions. Capital N is the number of incommensurate tones used to drive the system. Hopping models in capital N dimensions with an electric field, which is now this vector. Yes.
If I get quasi eigenenergy epsilon alpha, like they are not periodic, like are they periodic or they are periodic from omega?
Yeah, so good question. What will happen is that these quasi-energies, the quasi-energies now become hard to understand because the way we're talking about it. So maybe let me draw. You're gonna see more pictures of these, but just to give a concrete example to answer that question. So the simplest example, and we'll build it up again, will be a qubit driven by 2 tones. When we do that, we'll get a 2-dimensional lattice. Square lattice, there will be a general electric field. And now in response to your question, what's going to happen is that when I think about this, that I'm still going to have only 2 solutions. But when I look at the Stark ladder, there's going to be 2 ladders with 2 very incommensurate frequencies. So the quasi-energies will densely fill the space. So they become hard to talk about. And in fact, I won't talk about them, right? For this reason. But the quasi-energy states and their properties, that's what I'm after. Is there another question? No? Okay. Yeah.
really reminds me of. There is where we have like functions which are periodic in one direction, another direction by some number tau, and you get verified.
It is related. In fact, that's how we solve, when we actually, when we numerically investigate these systems and solve for these quantitative, that's how we do it. We put it on a torus with, but it has two periodicities. So when you have the time, you look at what time evolution does to this function defined on a line when you go through a period of the other one. Yes. That's how you find solutions. Yeah. So yes, closely related. Okay. So that's it. I just want to write this on the board, and now I want to tell you why this is an interesting thing to do. Right? Just seems like, sure, we can do it, but why do it? One thing I will come back to is, notice I just wrote here try. It's just like I'm trying to plug it in. And we'll come back to it asking, what does it mean that these solutions exist or not? Okay, and a particular feature of that is basically in which settings will we be able to find solutions, special solutions to time-dependent Schrodinger equation, where up to a phase, they have a smooth dependence on the drive phases. And we'll come back to this in the next lecture. But first, let's look at phenomena, and then we'll pick it up again.
Time-independent equation.
Say that again.
What time-independent equation gives you eigenvalues?
It's the same thing I wrote. It's the one with the hopping one, except now you'll get. I'll do one pictorially for the one I have, but exactly. Yeah. But we'll do some picture example of that again. Okay, so I'm switching to slides. I have some, hopefully not inordinately large number, but please don't use, I know people, and including I, can go very fast at slides. So please slow me down. You don't have to cover everything in here. I can also choose to cover different things. So yeah, let's not I keep asking questions. Okay, so here's the plan. I want to describe to you a particular example, which is the simplest one beyond going beyond the Fluke that we talked about yesterday. Is this thing all, does it work? Nope. That one? Yeah. Okay. And so I want to describe to you the two-tone driven qubit. And I want to tell you why it's interesting, basically, as well as an interesting application that's motivating experiments to realize this in superconducting qubits. And then I will start building towards the idea of this is only a particular example of a broader class of things we can find in these multi-tone driven systems. Okay. Okay. So always good to start with a Hamiltonian. Let's do that. So concretely, this is the kind of system for which I'll show you dynamics as well as what happens. We have two levels. We're writing the Hamiltonian as a B dot sigma. You can always do that for a two-level system. Really, you should call this a two-tone driven qubit. It may not be a physical spin. But what are the features of our drive? You see immediately there's two frequencies now in the game. There is one frequency driving the X and the Z field. If you thought of this in space, it would be circular polarization because in X and Z, right? Because one is sine, the other is cosine. There's a second frequency, which you can think of as a circularly polarized drive in the Y-Z plane. And finally, we have the fact that our qubit has a static splitting in the Z direction in the absence of all these drives. Okay. Okay. And now the observable of interest is going to be something we did not have when we had only one drive, which is we're going to look at the total rate of change of energy in the system. That's fine, that we had before. but now it's going to be a sum of two parts. It's going to be the rate of change of energy in it because of work done by the first drive and because of work done by the second drive, right? And so in particular, we can look at this total as a sum of two pieces. What is the power from drive one? What's the power from drive two? Now, the fact that this is a bounded system, we said this yesterday, means that you can't, just because you make one drive two doesn't mean that you can suddenly pump arbitrarily amounts of energy in it. And that doesn't matter which Hamiltonian you use here, H naught or H. So when you time average, that's this over bar, this better be zero. But there's two ways two quantities can add up to zero. They could either both be zero or they could cancel each other, right? And that's what we're gonna see. So I'll start to, this is the reason I do the slides, by the way. My former postdoc Phil made this animation once, and then I'm always like, oh, I love this animation. So then, okay, so what are we gonna do? I'm gonna go in a minute, but just to orient you, these are two values of the static field on the spin. Okay, so for the parameters that were chosen, just to flash the Hamiltonian one more time, notice that I picked units where the amplitude of the drives are 1. So when you start to see these things that are 3, etc., what we're comparing it to is the amplitude of the drives. Okay, yeah. Yeah, so it just a time average longer than both their periods, much longer than both their periods. Yeah. What you mean? What is it? So formally, a time it should be a time average of a quantity will be take that quantity, integrate it for an observation window that is much longer than the periods of both of the drives, and look at its value. Yeah. Okay. Compute it. Oh, just so think of this as this will be, and it's easy to actually write it down for the system. This is simply some time-dependent operator. And so I guess there's two things going on. There is, it's maybe easiest to think in the Schrodinger picture. So because our operators have explicit time dependence and our states will evolve in time with the time-changing Hamiltonian. So does that help? You could also plug everything into the Heisenberg picture too, but then at every instant of time, your operator is different. So yeah, there's a bunch of time dependence in here. We're gonna average all of it by doing this, by that. Okay, so whatever it is, this thing could have time dependence coming from for all kinds of reasons, because the state evolving, the operator changing, you just average everything. Oh, yeah, the other thing that was it. Yeah.
So as a function of theta, there's this gradient.
Yeah.
But if you think of it as a function of time, it's never periodic.
Yes. Yeah.
So I guess that's
yes. Yeah. So when I say
lattice is there, but it's not, you know, as a trajectory in time, you don't go through the lattice.
you'll get arbitrarily close to any point in theta. But yeah, indeed, like, I mean, if I was being, you know, this is true for the Hamiltonian. But formally, when I'm looking at time, the solutions, I'm evaluating it on a trajectory on this torus, which gets arbitrarily close to any given point. But I guess the content of the solution is really that there is a smooth function that you can define on the entire torus that you are sampling from in time when you do the solution.
And then you take a trajectory through that.
Yes, yeah, and it is that smooth function as a function of theta that you are Fourier transforming to get the frequency lapse. Yeah.
I think about this as like a variation of exact time.
We can actually find solutions, but I'll have to tell you in what cases. So lecture 3. Yeah.
I just wanted to understand the equation better. So you said that there are two time dependencies in the rho and the Hamiltonian cell.
Right.
Shouldn't there be two more terms where you're just the time derivative of the rho evaluated with the original Hamiltonian? imagine the H, expectation value as space of rho and H. And then rho will have its own time derivative and H.
Oh, I see. So you're worrying about an H naught part with the because of the time. So yeah, I'll actually have to think. You're right that might be there. It won't survive the time average. So what you'll see, I'm just going to show this in a minute. What I'm really looking for is large amount, and by large I mean large compared to the energy scales in the qubit. I'm on a work done by the first drive that goes on into the second drive, and the qubit in between is just going. So you're right, there might be an extra piece formally that I should write, depending on what quantity I'm evaluating here, but it's not going to survive the time average I'm after. Okay. Yeah.
I didn't quite feel
The question?
the question, but maybe related to that. Comment on this one. You have a time derivative average of age.
Yeah.
Using Feynman Helmholtz. Like,
Oh,
there's time derivatives on the
yes.
states as well. So they're orthogonal.
No, so actually, let me.
So if you let's say you're in the turning the picture.
Yeah.
The time derivative on the average is an expectation value. The time derivative from age is supposed to be plus that derivative with the wave function.
Yes. Yeah.
Typically, you thought there's a way. In the non-derivative.
Yeah. Yeah. So actually, no. So that's exactly what he asked. So no, I think this equation as written is correct for the pieces that will survive time average. It's wrong as written. This is wrong because of the piece that you just said. There is a piece that is, so when you have driven systems, it doesn't go away. Isn't and can have an overlap with the state. Yeah, can have the overlap state. And so, but what that is a piece that is, kind of, if you just think in terms of energy, if there's energy coming in from drive 1, it can go into the qubit and drive 2. And that's kind of what I'm trying, but the total energy in the qubit time average doesn't survive. So that's all I'm trying to keep track of. Yeah. So I think maybe, so I'll ponder if this equation as written is correct. It does seem that it's missing a term, but I think this equation as written is correct. That's what I would say. Okay. And actually, maybe I should show this. This is giving you guys, I'm not time averaging at all here. So what's being shown here is the work done on each of these, on each of the drives as a function of time, which is actually not without these time averages, just evaluating formally the operators corresponding to this work. And there's clearly two cases. Maybe I'll just let it run and run it again. So let me first talk about this work and then what the qubit did in between. So when the bare splitting was comparable to the amplitudes of the drives, we see this interesting setting where one of the drives is doing linearly, on average, linearly increasing amount of work as a function of time. The other is it's decreasing such that they add up to 0. Whereas this is the case when the splitting on the qubit, bare splitting the qubit is too large as compared to the drives, where on time average, they're not doing anything interesting. Each of them is not doing anything interesting, okay? So it is this regime that we're interested in, and which is something new that we can have with multi-tones, which we could not have with one tone, because with one tone, like we said, you cannot, there's nowhere for the energy to go. The drive can't keep doing work because we have a bounded system. Now it can, because it can go to the other drive. Yeah. I don't know if I have a longer time. Here, that might help. There's a peculiar, that was one trajectory. What these are many different possible initial conditions that you can start with, and showing you that all of them do this. And in particular here, that particular drift you saw, I think doesn't survive. Only if I time average. So it's because I didn't time average here. I'm literally showing you the thing. So actually, speaking to the point that everybody raised, you can see that there is what you might call micromotion on top of this average slope. It is that piece that's the energy going into and out of the qubit. which was the piece that was possibly missing in the previous thing I wrote. So that's this wiggly stuff, but the average thing is what we were talking about.
Physically, you moving, well, physically, but you moving to the lattice, that's what the work is?
I'll give you a picture in a minute. You're absorbing photons, yeah. So physically you move to the lattice. Yes. 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 No, you can't have it for a bounded system because of Stark localization. No, in it, there's an extra dimension. So we're going to be talking about perpendicular to the Stark. Yeah. I know in this one it does. I don't think it's statistically significant in the sense that it won't survive. Like this is only 20 periods. It doesn't survive the time average for a longer one. Yeah.
What side, which drive gains energy from these things?
Good question. The state of the qubit. We'll talk about that also. Did I? Okay. But this is a phenomenon. Okay. So whether or not we'll like make analogies and start to explain it, but hopefully it's clear what we're trying to explain. What we're trying to do. And I guess the qubit animation, I didn't say much about it. The only thing to have taken away was in this case, the qubit state appears to just qualitatively explore the whole block sphere. Whereas here, if you looked at it, it would be buzzing around the z-axis. Kind of makes sense because the z field here, static z field here is larger. So mostly the qubit, the drive just causes some buzz. Whereas here it's exploiting the time block sphere. Okay. Okay. So and now of course, those are for two values of static fields. And now this is the time average power. So that's slope time averaged. I apologize, this should have been units here, but okay, so there's one was non-zero, one was zero. And now you can fill this in. Thankfully, extremely easy to do that numerics on a two-level system. And you'll find something like this. So it'll appear to be that there is an entire parameter regime in which you get the same value of that slope that we saw. So that's when we'll say it's quantized. This is what we mean. Doesn't change with various perturbations that you can make. Then there is an abrupt transition at which actually, I won't talk about this, but we can talk, it's half the value over there as you see in the phase, and then it goes to zero. Okay. Yeah. Yes, I will put up formula in just a minute. Yeah. Instead of what, sorry? Yeah. The value of BZ. Okay, actually not quite. The scale of the instantaneous Hamiltonian. So BZ, the amplitudes of the drives, all of them. Right. I mean, you can right. We can write down a formula for it to get a scale, and it will follow that. Right. And because it is very much the energy that's going in and out of the qubit, so that means its energy scale is set by some of the instantaneous Hamiltonian scale. Yeah.
How does it depend on omega 1 and omega 2?
Okay. Two more slides. Okay, so let me keep going as you guys are clearly ahead of the game. So in what follows, I will both give you formulae explicitly on omega 1 and omega 2 and such, but also really try to ask ourselves, what was it about the Hamiltonian we chose, and that led to this response? When should we expect it? And we build outwards from there. Where is it coming from? Why should a single qubit exhibit a quantized response? Okay, and surprise, surprise, I've only said it 10 times. The way we can understand this is going to be in our associated static model with an electric field. And why? It's just because like we said yesterday, we have a lot of tools, well-developed tools in band theory and condensed matter for understanding the physics of static band structures. even in an electric field. And so we don't have to reinvent the wheel. We can take what's been learned and understood here and translate it there to know what our non-equilibrium system is doing. Okay, so that's what we'll be doing. To do that, let me build up the hopping model again. And I'll do it this time from the perspective that we've not yet used, but we mentioned once or twice. The idea that there is a meaning to these dimensions that we obtained in the frequency lattice, which is as photon numbers in each of the drives. Okay, so that's the perspective we'll use to derive it here, just so you can see the other way of getting it. So that perspective is related actually to this system. So it's a qubit connected to two cavities, which are dynamical degrees of freedom. And if this is then a representation of the state space of the entire system. If I told you how many photons are in cavity 1, cavity 2, and what has this been doing, we're in business to know that's the entire state space, and you can describe any state of this joint system with that on this lattice, right? If I told you amplitudes on this lattice. So then just to state it explicitly, it's a 2D lattice. It's got two boundaries, and it's got two levels per lattice site because we're thinking about qubits. Okay, so now it's easy to derive the hopping models we got here coming from this perspective. So first is if we had a term that just has to do with the qubit. I don't know. I guess in the example we had, this should have been as z. Then this is simply a static term that is the same on all sides of this lattice. Okay, that's fine. Now we can think about terms that involve an interaction with the first cavity. That is the A dagger here. So I've even written out a term that doesn't appear to conserve the total, like it does. You flip the spin and you absorb a photon. Okay. And then, so that's easy. So that gives us hops on this lattice because you do something to the internal degree of freedom and you hop left or you hop right. Hopping right, permission conjugate, hopping left. And now you see I've colored all these hops. And this was because in this cavity system, there are Bose enhancement factors due to A dagger acting on N is root N plus 1, N plus 1. I think I have the N plus 1 in the right place, but whatever, right? You see that at large N is a square root N dependence. So going from left to right, these hops are getting stronger. Okay, so unlike what we had yesterday, this is we're in the process of building up a spatially inhomogeneous hopping model. And same thing, same stuff. Now y direction because of interactions with the second cavity. And finally, photon energies for photons in the first and the second cavity can be encoded through this uniform electric field that we've discovered in the classical limit as well. And here, is just accounting for photon energy.
Why is the hopping in the second cavity excitation number conserving, but not in the first?
Doesn't have to be. I simply picked terms that if I took the Hamiltonian that I'd written down classically and I quantized it, I will get terms like this. So I put it down there to emphasize that those kinds of terms are necessary in the two cavity level. Does that make sense? Maybe, yeah. It could, generically, they both can have it, yeah. So there's many choices. You can make some choices. It's a little bit this SX thing here. You can make some choices in which it just looks like Jaynes Cummings in one, and then the other has these terms. And in fact, in the experiment that I'm going to describe to you, that's what we do. So it's a Jaynes Cummings. So for those of you who don't know what that means, this kind of interaction term is called Jaynes Cummings. I guess things in physics are always named after people, right? And if you don't know that, then too bad, because you'll never know what you're talking about. But yeah, it's just this term has a name called Jaynes Cummings, and this is often the term that is most available in a coupled cavity atom/cavity qubit system. No.
all talking through all this thing. So why does it have a stronger Hawking as opposed to larger? What make it?
So yesterday we derived the frequency lattice model in the classical drive limit, in which we did not have a dynamical cavity that could respond to changes in the qubit, right? And so you can obtain that. So this problem contains the physics of the classical problem, in the sense that we can take a classical limit that goes deep into the bulk of this lattice and take an appropriate limit of large photon number and inability to distinguish n and n+1, and we would recover our homogeneous hopping model in the presence of an electric field. Yeah. Yes, yeah. So I used X, Z, and Y, Z. So you cannot have, you must have at least in one of the cavities non-conserving. Yes. But let me just say, that's because I put it in a planar geometry. If you could do it in 3D as a genuine circular polarization, then it need not be. So it depends also how you're implementing it. As a planar cavity, yes. If this is all in the plane, which is in the geometry for the superconducting qubits, yes, one would need these terms. Yeah. Yeah. So no, you have the same field. You have a correspondingly proportionally larger potential. The points denote, each point tells you what is the photon number in 1, what's the photon number in 2, and the internal degree of freedom tells you the qubit. Oh, that's just bad drawing skills. Yeah, sorry. Maybe I shouldn't do slides. Then you wouldn't have picked up on it. Yeah, this is a poor keynote placing skills. Okay, but yeah, sorry. I've never gotten that question before, but now I know. This is bad. All right. Yeah.
Could you explain again why you got the non-number concept?
Oh, these ones?
No,
Oh, this one?
Yes. Why do you get that?
It's because the classical Hamiltonian I had one frequency acting in the XZ plane and the other in the YZ plane. When you go through and quantize those drives, at least one of them has to have these terms. Okay, that's neither here nor there.
This has to be the case.
No, it doesn't have to be one doesn't need to have this term. It depends a little bit on what the physical geometry of your cavity qubit system is. So perhaps it's a bit, maybe it's a little bit of red herring to put this up, because maybe it's more confusing than useful. Yes. Yes, no, this is all in the rotating frame. Is that what you mean? Yeah. Yes. Yeah.
The viewpoint of open quantum system with the photon bells in the cavity, can we say it contains no Markovian quantum effects in the cavity?
Or I think a helpful way to think about what I'm going to describe is that the strongly coupled qubit to the two cavities gives you, it makes the cavities nonlinear enough that you're able to do frequency conversion. What's that? Yes. Yeah. Yeah. So the qubit is the key nonlinear element. You're strongly coupled to that, and that is what is allowing you to do this nonlinear process, which is changing frequency. Yeah.
So is there significance that the one tone is rotating on one axis, the other one?
Yes. Yeah. Yes. Yeah.
It will both around the same axis.
It would not. We wouldn't have it. No. And this is okay. You guys, maybe I should keep going, but it has to do. Let me keep going, and you ask again if it's not clear why. All right. So I already said this, and at this rate, I won't ever get to showing you guys how to get this. So let me keep going. All right. So So wonderful, we've built this lattice, and now it's time to try to use it. So for a moment, let's ignore the electric field, because if we ignore it and we work in this classical limit of ignoring the back action of the drives, then we have a translationally invariant 2D tight binding model on a square lattice. Even I know how to solve that. You get block bands. But those block bands that you get can, in general, there's two of them because we have two orbitals per site. They can have Chern numbers. Okay, so I'm not going to go into great detail about what this quantity is and how to understand it more broadly. But this for our we'll come to the specific physics this implies for our system, which is most important. But it's basically an invariant. It's an integer. It is something which is a property of an entire band. Okay, and it can be 0 or it can be non-zero. And if it's non-zero, it has to add up to 0 between our two bands. Okay, so fine, that's some thing. It can be there. So what? And so what for us is that the physical consequence, which is going to lead to the thing we already saw, is that wave packets are going to move on this lattice in the presence of a weak electric field. Just to give you a punchline so you can follow what's coming. They're going to move on, this Chern number is going to induce on average an transverse velocity for wave packets on this lattice. And if it has an average transverse velocity, then you could see that photon number in mode 1 is going down and mode 2 is going up. And that is it. That's what we're going to be after.
Is it basically hopping on an equipotential line with respect to the electric field?
As intuitively, yes. In detail, no. Because the fact that our, I didn't emphasize it, the fact that our frequencies are incommensurate means that our electric field not pointed along a lattice direction. So you can draw it perpendicular to it, and at most one lattice point will be on it. Right? But you can certainly think about lattice points closest to that equipotential and try to understand physics. Yeah. So say that again. You will bounce, but if we have time in the end, I'll describe all that. Yeah. Other things happen clearly because you cannot deplete the mode beyond 0. Okay, but let me explain this to you guys because it's actually pretty simple and it follows from simple semi-classics of wave packets. So what is a wave packet? Simple enough. It's something that lets us talk about both the mean position and the mean momentum. And Gaussian wave packets in both. It's a wave packet is something that lets us has a position in R vector and K vector space and has a velocity in both spaces. So when we write equations for the motion of wave packets, we're going to describe how it moves in this space and this space, right? So there's two coupled equations for wave packets. One is easy to understand, which is that this is the version of Newton's equation. dp dt, rate of change of momentum, is due to all the forces in the system, either due to an electric field, or if there's an external magnetic field, then this is a Lorentz force, right? So that's easy. The more interesting one in lattice systems is this. So the first part here is just tells you that the velocity in space is determined by the group velocity due to the dispersion of the band. That's this piece. And the second piece here is known as the anomalous velocity. It's the version of the Lorentz force that you have in K-space in real space. Okay. I'll just use it. I'm not going to, like I said, I'm not going to go into all the details of this. So these are the wave packet, the equations, which we can use in our 2D lattice. Let's use it for our specific problem. So the one that's easy for us, we have no magnetic fields. We just had an electric field in our 2D lattice. So this equation is easy, and you can solve it. If you solve it, you basically obtain that kx and ky move deterministically in time for our wave packet, and according to these this time evolution, and so if you plotted that out, so this is the Brouillon zone. Stop me if I'm losing all of you. I don't keep changing spaces. So just to say it once, I'm doing wave packet dynamics where I call this real space, and that is then my Brouillon zone. Okay, that's the reciprocal space. And I'm talking about a wave packet that has, for which I can specify position in both lattices. And now, so I'm saying that in the Brillouin zone, because it's just uniform electric field motion, the wave packet motion is simple. But in particular, what it does is as you keep going in time, it covers the whole torus. So when we do this translation from lattice effects, from things we understand to our dynamics, this is the big difference it's going to do. When we have an integral over K space, or the Brillouin zone, we replace it with a time integral, okay? This is where our time average is coming from in the quantities that we had. So that was this equation. Now we go back to this equation, forget this term for a minute. Let's focus on this one. What this term is a term known as something known as Berry curvature that's intrinsic, determined by the band, fine. But look at this thing, K dot is the electric field. So it's basically something that gives motion of the wave packet transverse to the electric field. So omega points, for vector notation, it's pointing out of this plane. Electric field has a direction, and this is transverse to both. And so it's going to be perpendicular to the electric field. Okay, so yeah.
Omega again.
So this is the Berry curvature, and it is like a magnetic field for real space wave packet motion. It acts in that way. Okay. Now, long story short, this Berry curvature integrated magnetic field in these equations is quantized. That's exactly what the Chern number is. So once you go through, that's telling you something about the transverse velocities properties that's time averaged and quantized. And this is in the end, the bottom line for our wave packet motion. If you analyze those equations, you find on average, it moves transverse to the electric field, but not by any old amount, but by an amount that is quantized in units of the period of one of the drives. So people ask me, what was the formula for the power? This is it. So I'll just say this out in words. What this is saying is the average photon number transferred to drive 2 is integer numbers per period of drive 1. So on average, you transfer C photons per period of the first drive into the second drive. Okay, and C is an integer known as a Chern number that you can work out from the underlying band structure. Yeah, did you? I'm sorry, I can't hear it. I'm treating the electric field as conservative, perturbative. Yes, yeah, yes. So hold that thought. I'll tell you. That's why I call. Oh, no, it depends. So remember I'm so sorry. It should have been little omega vector. No, remember the electric field is something in this model. It is the drive frequencies we choose. So we can choose drive frequencies that have a separation of scales with the other scales in the problem. And then we can tune this to be in the weak electric field regime of this model. So it is under our control. Relatively small as compared to the other scales in the problem for this effect. Yeah. Yeah. Yes. So it is this drive torus that is just the reciprocal space. That's it. So it's just the phases, and that's what we derived, right? We just said kx is omega 1t, k. It's just relabeling what I called a theta torus before. Yeah.
The usual band structure, I understand that you had time and you had periodicity in space. Fourier transform periodicity in space, you get Brillouin zones, and you can write down semi-classics. Right now, your periodicities are in time, in phases.
Yeah.
Then you have R dots. So I'm really confused how the equations are exactly the same.
Yeah. So it's a little confusing. You have to do, we're really thinking about a wave packet of initial conditions of our qubit moving on the drive.
So you're working in a space of time and phase.
No, it's better. It's easier to think about. We're working when I said we had a wave packet in both, right? So what do I mean? What I really mean is you have a wave packet of initial conditions, which you can tune by tuning. I had these two drives, omega-1, sine omega-1 t. There's a relative phase between them, which is not well defined, but you can tune it. You can start at different points in that time evolution. And that it gives you a packet of initial conditions at different drive phases that you start at. That is a wave packet that you want to think about. Yeah. Yeah, it's a good question. And someone also asked me before, how do we know which way it pumps? So now I can answer this question. Actually, let me just put this out here. So I can now answer this question. So remember, we had two bands, and the two band, which band you're in is determined by the orbital state you pick, which is our qubit state physically. So if we prepare a qubit physical state to be such that in this picture, we're in one of the bands, the turn number will be of one sign and we'll get current positive. If we prepare the opposite state, it will have weight on the other band, it will be in the negative. If we prepare a superposition state, which is easy to do, then we will find on average 0 photon current, but growing variance in time. And you can play games. Superposition states are kind of interesting, but they will be more fragile because you will be creating macroscopically distinct photon states in your cavity as it propagates in time, right? But it's interesting to do. And at this level, yes, it'll work. Yeah. T1 is the period of the first drive. Yeah. Yes. So I'll talk about it briefly. So short answer, this level, this effect persists. This transverse velocity effect persists.
The usual real space, if I have and I'm working with bands that have a non-trivial number, I usually have the idea that if I were to take that system and place it on a finite lattice, it would actually be at states that can be. What does it need to have? Is that technology also sort of pass over here? What does it mean to have it?
Hold that thought. I will soon draw sketches of what do the quasi-energy states look like on this lattice. And it's not about edge states.
So, if you write an equation for N1 dot,
It would be negative
it would be negative, but it's,
C on T.
is it also, you also have 1 over T2 times same C?
Same C. Yeah. Basically, because
The difference is the energy from the bomb.
so basically omega-1 N1 dot plus omega-2 N2 dot should be 0, which is total energy in the first drive plus total energy. So and that's why it's the same C. So the on average, this amount of energy is coming out from the first drive and going into the second, or vice versa. Yeah. Not fraction, integer. This is an integer per period of the. Yeah. 2.
But in that same period, it's 1.
So they're not commensurate drives. So it's hard to think in one unit of the drive, because indeed in one drive period, it looks like the other one is lost fractional, but on average, they will equal. Okay, let me keep going. So that there is this kind of effect was actually first pointed out by these authors in 2017. They called it topological frequency conversion. We can now unpack that topological because there's an origin through this frequency lattice to a topological invariant frequency conversion, because you're changing you're changing energy from between one cavity to the other, which have two very different frequencies. In general, not in general, for us, irrationally related, right? So that's a part of it's a non-linear device in which you're converting photons from one frequency to the other. And this is where this average slope came from, this motion on the frequency lattice. Maybe in the interest of time, I could skip this. One or two of you asked, okay, so I'll maybe address one or two things that came up as questions. first, someone was saying, pointed out that this is a linear response effect. It is. And so there is a question about how to think about this. If I cannot ignore the electric field, remember I started with bands of my 2D lattice, which is throwing away the electric field. Whereas yesterday we spent all this time saying along the electric field direction, you'll have Stark localization. So you might say, okay, maybe it doesn't persist at all. So short answer, no, you can think you can have a finite electric field and understand where this effect comes from. And then you have states that are Stark localized in one direction and they are delocalized and current carrying in the other direction. So that's in response to your question. These are not edge states. They are bulk states, which are current carrying and delocalized on the frequency lattice. They're localized in the direction of the electric field. So this is a picture of them. These are what a quasi-energy states look like in order that you can have this effect of topology, frequency conversion. I'll skip this. If someone's interested, we can in this picture find the right invariant that will determine the average current carried by these states. Okay, you guys have asked a lot of questions. Any? Yeah.
Can you still give the bands that have not you need that
So now I can come to some questions people ask me. So now you know exactly what you need, at least in the small frequency driving regime. You need the 2D bands that you have to have Chern numbers, which means you need to have a time reversal breaking on this 2D lattice. So your K models need to be complex in a base. So that's it. Someone asking me, do you need that? Will that be important? And yes, without that, you won't have this effect. Part of why, if you were putting both drives in the same quadratures, X and Z, it won't work. You need to be using X, Y, and Z. Is there, yeah. Yeah. So if you treat the Berry curvature as a flux in this lattice, it's perpendicular. Yeah, that's right. So sorry, I should have said this. This is physics accompanying the integer quantum Hall effect. If in case that yeah, just to make that connection explicit. Yeah.
Also, initial state of Boltzmann freedom, that picture. Well, why does it start from that?
Oh, here.
Yeah.
So first of all, you can in second quantize you can prepare your system to be in whatever.
But original picture there's no photon.
Yeah, original picture there's no photons. So then there's this is just okay. So let me address that too. This is deep in the bulk of the lattice. This is one family of states, and you'll have all its Stark shifted copies, and there'll be one more kind of state which pumps the other way, and all its Stark copies. Yeah, there's no origin of where it starts. This is like going on both directions ad infinitum for that model. Yeah. Yes. Yeah. In some, yes, if this worked, yeah. Yes. Yeah, just hold that thought. I'll show you some pictures of what happens in the cavity. Okay. Yeah, so like right now. So let's go. Several people asked what if you go to the cavity? And so let's do it. I'll both show you numerical simulations as well as an interesting effect that's motivating some experiments to try to actually see this. So an interesting application of this is not just to pump energy, but to create specific non-classical states of light. Okay, so in particular, using this energy current coming into the cavity, say you can, what I'm going to show you is that you can boost states, by which I mean, if you started with a Fox state with low photon number, you can go to a Fox state with higher photon number at certain specific times. And so that is a kind of resource, by which I mean you need the ability to make these kinds of states, certainly to beat the Heisenberg limit of sensing, to do more with quantum systems as compared to classical systems in terms of their sensitivity, but also for certain ways of doing quantum computations using cavities relies on your ability to make non-classical states. Okay, so this is an interesting thing to do and a hard thing to do. So what is it, and why does it happen from the things we've said? So we discussed this, and we have we described why we had this current, and now we're going to go to this limit. We still are going to treat one of the drives as classical, and the second one is going to be a cavity. The distinction in a real experiment is simply the quality factor. Everything in the experiment is a cavity, but the classical drive is a very leaky cavity in which you can drive it well, and it like quick, out comes a current. There's nothing hanging out in there. Whereas this is a high quality factor cavity, so there's a photon can bounce many times in here, interacting with the qubit before you lose it. Okay, and that's the distinction. And what we're going to do is we're going to set it up in a regime where energy current should come into this cavity. And I'm going to show you that if you start, this is what boosting is. I'll show it for the Fock state example. But if you start with your initial state of your qubit in some direction, and in a product state with your cavity prepared in some state, at special times, the qubit will come back to nearly the same state, but the cavity state is now boosted in the sense that you have the same coefficients, but now about a mean value of photon number that's just shifted. Okay, so boosting is on the Fock space lattice. And so if you started with a single Fock state, now you're just at a larger Fock state. Okay. Let me skip this because I guys want to show you guys this. So this is in response to various things. What does it look like for the cavity, micromotion? So this is a numerical simulation. I skipped the Hamiltonian. I'm happy to go back to it, showing the physics of a cavity qubit and a classical drive in this regime in which there's an energy current going into the cavity. Okay, what's being plotted? Y-axis is photon number, x-axis is time in units of the classical drive frequency. I apologize. We keep shifting capital omega and little omega between every time we write about this, which is bad. But yeah, okay. And the color code is telling you that if what is the probability of having different photon numbers in the state of the cavity at that instant of time. So these are in general mixed states because we have a cavity qubit system that's strongly coupled, and we're looking at the density matrix of the cavity and asking for the probability distribution of different photon numbers. Okay, and finally, this is on a log scale to really bring out differences, so you can see, you can see more. Okay, first things first. There's the promised pumping with the, and in fact, I drew this line correct to scale. It exactly has this slope for the, with the numbers picked here, okay? So this was our energy pumping effect, what they call topological frequency conversion. So in response to various people, it survives in the cavity limit, even with these inhomogeneities in there. Okay, so that's good. There's an average slope. Then in response to the other question, notice there's a lot of stuff going on top. So indeed, there's micromotion. It's not just like it marches up. But then micromotion is kind of interesting because you can see that there are quasi-periodic in time rephasics. So this is a distribution, remember. So you start with a narrow distribution in broadened and photon number space, but then it recoheres at some special points in time. When it recoheres, it's forming a nearly Fock state with a much larger photon number. And that's what we're calling cavity state boosting. Makes sense? Okay. Yeah. They are integer multiples of. Yeah. No. So what should, I have a little bit more time. Let me explain where it comes from, and then it'll be clear. Because we drew a bunch of blue arrows here. The blue arrows are theoretically predicted, and I can tell you how that came from, but you can also see where that it doesn't seem to point to other places where the, and you'll see why in a minute when I tell you how we got blue arrows. Yeah. Same thing that we said before. This is kind of the energy that's going into and out of the qubit. So, right, this is a cavity qubit, and the other drive. So basically in the middle, there's kind of, it's a joint state. They're talking to each other. Maybe there's some net energy in from the other drive. And then, yeah.
Sort of, I guess, how robust is the location of these blue arrows to like various stuff? I guess the average is kind of topologically protected, but like, if you're trying to precisely stop your thing at a time to like boost it a specific amount, like how, do those blue arrows move around a lot if you have some small arrows?
No, so that's actually a good question. So the answer to that is no, because they are locked to integers of the periods of the drive. So yeah, they so if you work them out, they are actually robust to small perturbations for that reason, because they're locked to certain integer values. Yeah. Original state, yes. Yeah. No, let me say why. Let me just say why instead of like leaving it all mysterious. So the origin of this is the term that I like threw out in my wave packet motion, which is coming from the thing that sets the group velocity. Okay, for the wave packet motion, we just focused on this part of the motion perpendicular to the electric field. But what about this? What this is going to do is it's going to cause block oscillations, and that's going to be the origin of the effect. So very quickly, what is block oscillations? So if you prepare a wave packet on a lattice in the presence of an electric field, it's pretty simple to show that it oscillates in space. And the oscillation period is set by the electric field strength. And as it oscillates in space, it also breeds, gets fatter and thinner and fatter and thinner. Okay, so this is called block oscillations. It is a manifestation of Stark localization, as we have said. Basically, all states are localized along the electric field direction. So if you prepare a wave packet, it can't get that far. It goes one direction, bounces, and back. So same origin, and this is what happens. So that's in 1D, easy to visualize. So we have that going on in 2D. I believe I have a crappy animation. Don't be confused by its crappiness. Okay, but hopefully things you took away was it was kind of, so it's slightly more complicated here because our electric field is not along a lattice direction. So that's why I drew my green thing kind of roughly going along it, but it doesn't go actually along it at any given, and yeah, it doesn't go, its motion doesn't line up with the direction of the electric field. But when we have two frequencies, there are special times called almost periods where both drive phases are multiple of 2 pi. Okay, so even though we may have picked them, the two frequencies to be incommensurate, at certain times they basically look commensurate. It looks like they both kind of come back to where they started, approximately. When that happens, that's when the wave packet rephases in our block oscillation game. So in addition to the fact that in that time it was also moving perpendicular to the electric field, that's our total effect of boosting. Did that make sense? So here's a joint picture of it. The wave packet, as it's moving, it has a net transverse motion, but while doing that, it's also doing these block oscillations. When the block oscillation period, almost period, lines up at those special times is when you get boosted states, because there you see only the effect of the transverse motion.
Is this basically when you're super close to a site?
Yeah, so the wave, indeed, it's hard to use wave. I'm using wave packet dynamics. It's not incorrect, but I'm applying it to pretty non-classical states like photon numbers, which indeed are delta function dots in this picture. Yeah. No, so which is why, I mean, there was approximates. So they never exactly return. they approximately return. And so these, where they're, if you look at the rephasings that we had, they're not infinitesimally thin. They're just pretty good Fock states, right? And then there's lots of more things you can say about it. The longer the time you wait, the better this rephasing, the tighter the packet. You can see this. The tighter the Fock state you make. Integer multiple of 2 pi, yeah, in both cases. And now coming to your question, blue arrows was because we can work these out, we can draw the blue arrows. Rational approximate, yes, yeah. Yes, yes. I'm not going to go into it, but yes, we looked at it, and then various things matter. So there, so at the most important thing, which is what we also see numerically, where there's a bunch more effects in the cavity qubit system, is that larger this almost period, better the degree to which they are 2 pi, better the rephasing, sharper the Fock state. And we can make that quantitative. How much better? What is the scaling? We can say that because we know how good the rational approximates are. Okay. So that was this. This I just put this in because of the comment David made yesterday, where we were talking about replacing classical drives with cavities and what effects may or may not be there. So this is just kind of neat to see. I didn't talk about what the qubit was doing at all. We were just focusing on the cavity. We could certainly ask what is going on between the cavity and the qubit. And one measure of that is to plot the entanglement entropy of the state of the qubit. Again, because they're talking to each other, this goes from mixed, pure, it can keep changing in time. So here is a curve in the same numerical simulation when we started our cavity in a coherent state. And you can see the qubit is not unentangled with it. I guess this is dimensionless, so I don't know, you have to decide how small is small, I guess. But it kind of reaches some value and it hangs out. This Fock state thing that we're doing, you see that we are actually maximally entangling the qubit in the middle. And then when we have these kind of rephasings, it goes back down. Comes back up and down, bounces back and down. Yeah, I don't know. Fun facts. Entanglement entropy doesn't always need to grow, I guess. But yeah, I don't know. It's this in these specific examples, even though we go from, maybe one takeaway message is even though we're going from externally imposed drives to dynamical drives, we can continue to describe that back reacting system with what we know from the external drive piece, in which this entanglement is formally just 0. That's what I wanted to say. Yeah.
But physically, the difference is whether, maybe mathematically, the difference here is whether you're treating the photon the drive classically, and that's what you call coherent state.
No, so this is we treated this is in the cavity qubit system where we initialize the instead of starting in a Fock state, you can initialize in a coherent state, and you can ask how much entanglement builds up. Okay, not a lot, and no features in time. You can start it in this Fock state, which is a pretty non-classical state. And then you see that entanglement gets maximally entangled, but then it like pops back down and up and down.
But the other thing, like thinking coherent state is closest to the
Classical driving, yeah.
Not entangled.
Yeah, so throwing out all back reaction would be 0. Keeping it in by doing the cavity QBD system gave us this much. And now with the coherent states, and then Fock is what we were doing to do this boosting, and we're popping the tree back.
You took the average occupation number in the coherent state larger and larger, so you expect it to be more and more like the external drive. You see the entanglement to go to 0.
Oh, here?
Yeah.
I feel like we did this, but I don't remember. I think, yes, that is what you expect, but I don't know if, off the top of my head, I don't remember if we check how well we checked it. Yeah. No, so let me just say one thing. I don't have any detailed answer to that per se, except for the fact that as you go to the right, remember you're pumping into the cavity. So there's more energy into the cavity, even though it's quasi-periodically becoming real Fock states. So it is better and better described by the classical drive scenario we had, even if it's not classical state. So things actually get sharper as you increase the photon number. Okay.
Only for the Fock state or other non-classical?
Any non-classical state that's narrow in photon number space. Yeah, right. And that's not basically it's relying because it's this. Remember, our intuition came from wave packets, and wave packets better be narrow in space. So if you made something that was too smeared out, you'll lose. Okay. Right. I'm going to skip this because there was a few rare experimentalists in the audience, but you guys, there's like 2 or 3 of you, I think. Talk to me after. I think these experiments are ongoing in Alicia Kolar's group at Maryland. Maybe I'll just flash this picture and then we'll keep going. This is kind of what it looks like. They are trying to do this with a transmon qubit. It's a particular type of architecture of a superconducting qubit. They have 2 kinds of cavities. This is the cavity that's higher quality factor that they're trying to pump photons into, and this is the one that they're using to both drive and read out. And in a rotating frame, they are realizing the Hamiltonian that we want because it's helpful to flash it once. And this is a very well loved, easily realized at this point type of cavity QED Hamiltonian in the rotating frame. Okay. All right. I'm going to, again, if you're really interested, I'm happy to do it, but somehow for this audience, I think it's all about new driven phases of matter. So let me do that last little bit. Speaking to things like how long does this thing live? Is this robust? And building outwards from here, thinking more generally about these multi-tone driven systems. So here's what I want to start building towards, which is that this thing that we just discussed, this kind of energy pumping effect with the topological origin, once you start thinking about spatially extended systems, we can really find these kinds of behaviors in the steady state and away from the low frequency limit. And to do that, let me go back to a picture here of what the quasi-energy states look like and why this cannot be a response in the steady state. By this, I mean the energy currents. So I already flashed this picture and I described it once. The quasi-energy states look like this. They are stark localized along the electric field direction, but they're delocalized infinitely in the classical limit, perpendicular to it. And not just delocalized, they're furthermore current carrying, right? And you need this because if wave packets need to move one way or the other way, there better be steady states that move one way or the other way. Otherwise, wave packets are not going to do it, okay? At least if you want it to happen in a steady state, you need this. So this is kind of pictorially what you need in order that you have this effect in the steady state. But you look at this picture immediately, and of course you must worry because you say, hey, there are states that are carrying current one way and the other way, and they're physically on top of each other. They're physically on top of each other. Anything you do to this picture, even if you could fine tune it, is going to couple them. And indeed it does, right? So what happens is even if you manage to fine tune to that point, which we know how to do, any perturbation away will eventually cause the 2 states to hybridize, resulting in 2 quasi-energy states that have, this is qualitative to give you an indication, but it has kind of circulating energy currents in it. It doesn't just pump one way or the other. It goes, if you made a wave packet, it'll go one way for a bit, turn around and come back. However, the time scales to turn around and come back are exponentially sensitive to scales in the problem, scales in the problem divided by the frequency. So there's a large window to do this. Experimentally, this is not what's going to limit them. So they're not worried about it. But formally, I'm a theorist. I like phases. And as a matter of principle, this is not a phase because it does not have a distinguishable signature in the steady state from just the other thing I showed you, which was crank up the Z field, have a spin just buzzing around. Okay. What's that? B here is a proxy for the instantaneous strength of the B field on the spin system. So it's some combination of the amplitudes of the drives and the static Z field. Okay. Oh, sorry, I'm going to skip that. About well, maybe all I want to show you is that, in fact, if you run, I showed you pictures only for maybe a couple of periods. If you run it for a very long time, you can see the fact that the energy starts to slosh. You pump it up to some point and then it starts turning around. Ask me more if you want to learn more about what that was. But what I want to show you is that, well, I want to ask and answer the question, yes, that can we create a steady state energy bump? And the answer is yes, in a kind of simple way. All we need to do is, the problem was that our two current carrying states were on the same place on the frequency lattice. If we could separate them, which is easy, add an extra dimension, physical space, then we could separate them to different points in physical space. No longer, now the extent to which they can talk to each other can be suppressed by their distance from each other on the lattice. And then that's the game to play to make this a real steady state response. So, okay, maybe I'll just flash this cartoon and then I'll stop and take questions. And so this is not just a picture. We can start from what we have, which is fine-tuned spins that can have these states lying on top of each other in the frequency lattice, and build this up by building couple layers models. So the way we do it is we associate the two spin states to the two states of a fermion on a site. And then we do what is, at least I've learned this trick from such constructions of the integer quantum Hall effect. There's a wire models of the integer quantum Hall effect. But we just do the same thing. You couple the state that pumps energy in the negative direction on one side, the state that pumps energy in the positive direction in the neighboring site. If you do this, you will end up with states like this. Again, I hope these pictures are clear. What these wiggly arrows are representations of this current that the state carries in the frequency dimensions, okay? And this is the space-like dimension. So when you do this, then in the frequency dimension, these guys just don't carry any current, but you're left with two edge states that are current carrying. And then based, again, from where they came from, we know exactly how much current they carry on average, and we know what topological invariant would characterize that. And so we can build models and study phase diagrams and study the transition from these kinds of systems. I think that was it. So I'm happy to take more questions, or I'm happy to say more about any specific thing.
How does that interaction with like 3M
Say that again?
That's like last module, you have like 3 dimensions.
Yes. So the full frequency lattice picture is this. So yeah. Well, so in the let me see if I have the full Hamiltonian. I don't have it written. So this is the form of it. So what are we doing? As a formal model, it has two spin states per site. It's a fermionic chain. We're only adding nearest neighbor coupling, but we're doing it in a very specific time-dependent way, such that it looks like we're coupling these modes that we're after. Now, that's so that we constructed the model here to exactly have the physics we wanted. But the good thing is, once you separate these modes, it's robust to making changes. So then you can take away this time dependence. Instead of it being arbitrarily Baroque, you can cut harmonics. You can make it simpler. Yeah. Yes.
The experimental setup for start. In the real experiment, there might be one more time scale of like also liquid thing. But you will assume that omega 1, omega 2 is small enough. So the period that can be large, but is it smaller than the liquid size?
No, that's good. So that's the reason why, they're not worried about this being a pre-thermal effect and such. Indeed. So the two things that will limit their experiment is the quality factor of the cavity, which is good. It's about 100,000, but it's not that good because 100,000 sounds pretty good, but 100,000 is for their gigahertz, 10 gigahertz photons. when we go back and say which frequencies are we going to pump at, those are in megahertz. So the conversion you're talking order 10 before you have to worry about losses. On the same time scale, the qubits dephasing becomes important. So these are the limiting things that will stop, which will kill this thing in the current architecture that they're demonstrating. But they hope to be able to show that they can pump a couple of photons. That's where the current realization is. So actually, as you asked, I think it's a step one. It's relatively easy for me as a theorist. It still has they have all the pieces to do it in the lab right now in some of the best studied qubit planar geometries. Down the line, if it's interesting, I think two things to do. They would in 3D, the cavities would be much better, and these could be much longer lived. And by building things like this, what you do, you not only you separate these modes, but I didn't emphasize it. Maybe it'll come with lecture 3. You can actually speed up the pumping rate much more. Because right now it's megahertz. Part of the reason it's megahertz is this various separation of scales in their problem, and we were relying on low frequencies, right? When you do the separation, you no longer need low frequencies. So you could hopefully pump in the gigahertz, and now you could really, get that 100,000 out from your quality factor. Yeah, but baby steps. Nobody, even though this is such a, I think, simple effect, nobody's demonstrated this in the lab, and I think that's the starting point. Yeah. So there's a so there's several things that are there. So first is if there is leakage, which there will be, and in fact it's proportional to the number of photons in the cavity, right? The rate.
More and more energy. That's called it.
No, so first thing first, when we study the dynamical cavity qubit system, we have this term. We allow for because we're really studying the model with the boson and everything. It's exactly as you say. As you pump energy into the cavity, the effective amplitude in a classical picture will go up, and it does. It's there. So one good thing is, in spite of all those effects being there, there's a robust slope, and there's these robust times we can predict in which we've ignored all those effects. Okay, just to say that's the nice thing about being topological in the sense that and relying on almost periods. These things are not very sensitive to you knowing the numbers of, as long as there's a phase or of parameter regime, and you're within that, those numbers don't change. The slope doesn't change, and the rephasing times, which are tied to the frequency ratios, don't change. Now, in response to another thing which I didn't talk about, is that classically, when you keep on increasing the amplitude, you will get out of the topological regime. So there is a maximum n you can pump up to, at which you'll start bouncing and more stuff happens. Yeah, but that again for the kind of system they're trying to realize in the lab is like 100 or something right now, and is irrelevant too. They will first lose photons because their cavity is not perfect.
All linear coupling still do that. Beyond the linear. Was it?
No, I think he was just saying that because you have this A dagger sigma minus, and as you pump more, the expectation value of A dagger goes up in time.
Well, it
Yeah.
could be like A dagger, A square, whereas the flow. So non-linear coupling.
I'm not assuming we have them. Maybe there's some effective picture.
Model. There can be term like A dagger, A square.
Yeah.
Flow, something like that.
Right.
Non-linear.
Well, so in the rotating frame, maybe it's also helpful to say, in the rotating frame, our cavity and our qubit are near resonant. So it's not these kinds of dispersive shifts are not. Yeah. Important. I'll start there and I'll go. So yes, and Gil's group at Caltech has played games, interesting games with these. So as I've introduced it to you, it's always, every frequency is an extra dimension. That's true, but you can have, if you pick 3 frequencies that are have a relationship to one another. So you can play this game, and maybe you can see how it's going to go. If they're related to each other, then yes, you can write a 3D frequency lattice for them, but that's not useful. There's an effective 2D picture as a honeycomb lattice. They've done this before. You could do it that way, but the more natural way is that they have 3 related frequencies. And those 3 are like on this plane, they will sum up to 0, and then you can have a natural geometry for that. Yeah.
In the very beginning, you showed a plot that this pumping breaks down for some value of the magnetic field.
Yeah.
Why did it break down at the value of 2?
So that specific value you can derive from the associated 2D. So I said that this, everything was predicated on, gosh, I have so many slides. Yeah, it's predicated on these things having Chern numbers. So if you go look at the phase diagram of this thing, you can see that as you crank up the on-site splitting of the 2 orbitals, what'll happen is there'll be a phase transition through Dirac closing in which the bands touch, then they reemerge, and they'll have 0 Chern number. But from the perspective of the qubit, it's really easy to understand, because if you have a qubit, which a large splitting, and you weakly drive it, whatever tones you do, you can't do, interesting things. Yeah. The shape of what, sorry? Oh, the chip. So by the way, this is not their most recent chip, for whatever that's worth. But I'm happy. Oh. Sorry. Yeah. Robbie, is that what you which is that this is the Robbie coupling in this thing? Yeah, B0, yeah, sorry. 50 megahertz. So actually 50 is not because this thing as well is going to how do I want to say it? There's effective Rabi couplings that are time dependent because of how they're implementing this. So they need a dynamic range that's going between about 50 to 200 megahertz of Rabi couplings that they're using. So the bare one is lower so that you have the ability to strongly drive with this. This is another one. Yeah, B0 is about 50 megahertz. Yeah, so it's not in a very strong coupling regime for these frequencies. Yeah. I'll tell you the most general. So in the third lecture, I'll tell you the most general class of topological effects I know of, which is with no symmetry, like a class A classification, and there may be others with symmetries that we have not sorted out. Yeah. Yeah. So these things that I briefly only talked about are the multi-tone versions of the 2D Floquet topological insulator with no Chern numbers. So that's what I'll say next time. Lecture 3. Yeah. Yes, yeah. So they realize, all the bare frequencies for them is sorry, I don't know what happened. No, so it is, these are the bare frequencies and the qubit is tunable and stuff. So, but but what's going to be important are the micro, the 50 to 100 of megahertz amplitude and frequency modulation they're going to do coming in from this drive frequency, which is the time dependence in here in the frame. Yes, exactly. Yeah, but it's only order megahertz modulation. Yeah. Yeah, so that's the dream. I think the dream, like this is so you know, Alicia's her PhD was more in optical cavity QD, and now she's more superconducting. And it was her sense that, you know, the Rabi couplings are large here from the get-go. It's simple, and it's a simpler architecture if it was going to work at all to start to demonstrate it. But the place, if we can do this, that it's going to actually have, I think, impact is in the optical. So if we can actually take a cloud of atoms in a cavity and use the fact that we can get a cooperative effect for many atoms, because their Rabi coupling is way weaker per atom, that would be the dream. Yeah.
I'm still kind of can't quite decipher how the very curvature that leads to this effect of cupping.
Where is it in the?
Well, so like the two-dimensional space that in which you compute the curl of the Berry connection is kx and ky, let's say, which are the
Thetas.
Theta 1, theta 2.
Yeah.
So you need a curl there, so you need that to be non-trivial.
Yeah.
But where's the polarization of the drive?
Coming into that. Yeah. So actually, let me say that it's relatively easy to understand. Exactly as you said, you need integrated Berry curvature in this theta torus. Right. So the way you actually get it and why the drives are important is suddenly when we're in the low drive frequency regime, the instantaneous states are a good guide to what the qubit is doing. And the qubit's instantaneous states follow the states of the drive. So the drive is being used to put in that Berry curvature going around loops in the theta torus.
In order to have non-trivial Berry curvature,
yeah. In the block sphere as instantaneous states, that is imprinted by the drive.
Okay, so it's mapping what like A1, AX and Y on the block sphere.
Yes, yeah. 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 The whole block sphere. That's right. That's right. That's why you need X, Y, and Z polarizations of the drive to start to. These versions are a little bit for this stuff. You don't need. It's a little bit different. Now, no longer is it tied to Berry curvature on this torus. So
the equations that you were discussing.
Yeah.
Semi-classical, but it's all inside omega.
Yes, that's right. That's right. Yeah, that's right. Integrated non-trivial omega. Yeah. Well, Sagar should have been. Well, David's like, what about lunch?